Air enters a partially open valve inside a ventilator. A steady state flow of air is used to keep a patient's lungs open at 5 centimeters of water. The work rate required to keep the patient's lungs open is 1.9 kilowatts. If the inlet air temperature is 15 degrees Celsius, what is the required mass flow rate of air? Assume ideal gas for the air and a standard body temperature for the patient, neglecting kinetic and potential energy effects and any stray heat transfer with the surroundings. Okay, so we have a lot of assumptions that we're making here. We're going to start off with our energy rate balance equation. d E dt equals q dot minus w dot plus the summation of the mass flow rate at the inlet times the enthalpy at the inlet plus the velocity squared over 2 at the inlet plus the potential energy term at the inlet minus all that at the outlet. So here we know that we can cross out, rewriting our equation here, we can cross out dq dt because it says we are neglecting stray heat transfer with the surroundings. We do not want to cancel out work dot because we are given the work done by the ventilator. We are assuming that we are operating at steady state here because it says a steady state of flow of air. So that means that our m dot initial at the inlet is going to equal our m dot at the exit of the ventilator, which is our control volume, is the ventilator. And that also tells us that the energy entering and leaving the system is the same, is constant. So our whole equation here will be set equal to 0, or dE dt is equal to 0, you could say. So since we only have one inlet and one exit, I'm going to remove the sum term, and I'm just going to write, we'll write it as dm dt times h at the inlet minus h at the exit, because we are also neglecting kinetic and potential energy effects, which cancels out the v squared terms and the gz terms. And then this equation here is equal to 0. So we're looking for the mass flow rate. We have the work term. So all we need are our enthalpies at the inlet and the exit. These can be interpolated from our table because we know at point 1, T1 equals 15 degrees Celsius. And we know that the pressure is just the pressure at the atmospheric pressure. So P equals 103. And at point 2, we have T2 equals the internal body temperature of the patient, which for our standard body temperature for a patient in Celsius is 37 degrees Celsius. And we are going to say that our pressure equals 5 centimeters of water. Like so. That should be equals. Since we're dealing with air here and we are assuming that it is behaving as an ideal gas, we're going to take a look at table 822 and interpolate for our values for enthalpy. So we can find that H at the inlet is equal to 288.3 kilojoules per kilogram, sparing you the boring details of interpolation. Enthalpy at the exit comes out to 310.4 kilojoules per kilogram. And this makes sense because we have the same amount of mass flowing in and flowing out. The only change is that is increasing in temperature. So then we plug these two values into our equation here, which we can rearrange for m. So we get m dot equals work term divided by our difference in enthalpies between the inlet and the exit here. And now we plug in our values. So we have m dot equals, our work term is going to be negative because we are putting energy into our system. So we have negative 1.9 kilowatts divided by our difference in enthalpies, which we just found, 288.3 kilojoules per kilogram minus 310.4 kilojoules per kilogram. As you can see, there is a higher enthalpy at the exit than the inlet, which means that our answer is going on our denominator is going to come out negative, and our numerator is also negative, so we get a positive mass flow rate, which makes sense. And our mass flow rate is 86 grams per second. I'm now realizing that these pressures don't exactly correlate. This is a P total value, and this is a P gauge value. But we actually didn't end up needing to use the pressures. They turned out to be extraneous information because basically because the pressure difference is accounted for in other ways. Obviously, if we increase the mass flow rate, the pressure inside of the patient's lungs is going to increase. And the method that we would use to do that would be to increase the energy that we put into the ventilator. So the pressure is sort of implicitly, pressure difference is sort of implicitly accounted for there. Also, the pressure difference between the atmosphere and the patient's lungs is very small. 5 centimeters of water works out to 4.9 times 10 to the negative 3 bar, which would only affect our answer by a very small amount, even if we were to include it.